Now we're going to talk about a precise condition such that if the coefficient matrix A satisfies this condition, then there's at least one solution to the system A augmented with B for any B. Any B. So we have the following fact. Fact. Okay. So the following fact is there is at least one, there could be more, right? But there's at least one solution to A augmented with B for any B if and only if, so we see this if and only if showing up again, and this will, this will show up every once in a while. It's an important kind of statement to say about something. If and only if the rank of A is equal to the number of rows of A, and I'll say just row of A, and that means the number of rows in A. So you just count the number of rows, and that gives you this number. So the rank, of course, is always less than or equal to the number of rows, right? Because if you take the reduced row echelon form of something, you get the same number of rows, right? And the rank just counts the number of non-zero rows, right? So it can't be more than the number of rows. So this is always less than or equal to. But if the equality holds, right, that's the same as there being a solution, at least one, for any B you could choose. So that's actually a really cool fact. And let's do the proof of that. The proof is not so bad. So let's just follow along and do it. Well, so let's do the if part first. So if the rank of A is equal to the row of A, so if we want to show that there's a solution for any B, so if this is the case, then we have the following string of equalities and inequalities. Well, we have that the rank of A is equal to the number of rows, right, by hypothesis, rows of A. But that's also going to be equal to the number of rows in any augmented version of A. So whatever B was, this is true. And this quantity here, this is always greater than or equal to, just by definition, the rank of A, B. So that means that the rank of A is always greater than or equal to the rank of A augmented with B. But we also know that the rank of A is less than or equal to the rank of A augmented with B. We talked about that last time. This also holds. So I've got this has to be greater than or equal to a number, and it has to be less than or equal to the same number. So that number is the same. We have to have that rank of A is equal to the rank of A augmented with B for any B. Any B. And by our last fact, this means that there's a solution for any B. So for any B, we've got that the rank of A is equal to the rank of A augmented with B. That A, B has a solution. And that means we're done with the if part, right? So we've shown that rank of A equal row of A implies that this has a solution for any B. So for any B. And that covers the if part. Now we have to tackle the only if part. And again, what we're going to do is we're going to prove the contrapositive. Again, we use the contrapositive. So go look that up, and you can also you might call this flip and negate, right? Another kind of simple way to imagine what the contrapositive is. It's just a statement that's equivalent to an if-then statement, right? So if we use the contrapositive, well, we flip and then we negate, and the negation of rank A equals row A is rank of A does not equal to the rows, the number of rows of A. So, in particular, this means that the rank of A is actually strictly less than the number of rows of A, since the rank of A is less than or equal to the number of rows of A. Of course, that holds almost trivially, right? That holds trivially. The rank of A always has to be less than or equal to the number of rows. But then, the reduced, so we've got this rank of A is less than or equal, strictly less than the rows of A, but then the reduced row echelon form of A looks like so we reduce this A, and what are we going to get? Well, we're going to get a 1 here, right? So we have it's going to look roughly like this. I'm only going to draw three rows, but you get the idea in general. You know, I'll say I have a 0 here of some number here, say a 1 here, 0, 0. It'll be 0, 0, 0. Let's say I have a star here. I don't know what that is. Star here, and a star here. Actually, this has to be 0 as well, right? That has to be 0. And this could be anything, really. This guy could be anything, and that has to be 0. And then let's say I have this, right? So A, let's suppose this is A, the reduced row echelon form of A. Well, I can augment this with anything I really want, so I'm going to augment it with this, right? And of course, this situation is not solvable. I have a 0 is equal to 1 situation here, right? So this row, so in particular, this does not have a solution. Additionally, well, this doesn't have a solution, but also the process by which I obtained the reduced row echelon form is reversible because I just did elementary row operations. So if I reverse it, I'm going to get some, so reversing RREF after augmenting with ones, with a column of ones, gives us an augmented matrix. So we reverse it, we get A over here, and we get some B over here, whatever that is, that has no solution. Thus, we have a B such that this is not solvable, and so we've shown that there is a B such that there is no solution. And we conclude the proof with the tombstone.